Welcome, Randy. Randy, the floor is yours.
Okay, great. Thank you very much, Marcin. So I'm Randy May from Hazelcast. I'm an architect at Hazelcast, and my background is all basically consulting with Hazelcast, and I've been in this space, kind of in memory data grid type space, for more than 15 years. So I've worked with a lot of Java software developers, team leads, and architects on these sort of fast data problems. So today we're going to be talking about a concept that I'm starting to see a little bit more. I'm starting to see people like Confluent talking about it, and I'm going to tell you a little bit about it, why I think it makes sense, and also kind of a Hazelcast spin on it. So let's get started. Okay, so I mentioned so I'm going to do like a little prelude first. That we're going to talk about why it's important to call remote resources asynchronously. So it's super important. So I've done a lot of consulting on performance problems, and there's kind of two categories. One is, hey, I need this thing to have higher throughput, and our CPUs are nearly 100% utilized. That's actually a good thing. Usually, you may be able to profile and make the application more efficient, but it's really a good thing because that's what you're trying to do when you're writing scalable apps. Is you're trying to have them. You basically want to add throughput by adding CPU. That's kind of a success. But then the other half is we can only get, let's say, 100 transactions per second, and yeah, the CPUs are at like 8%. That's maybe the more common one, and I've seen it a fair amount, and it's result of basically things being over synchronized, that basically too much waiting happening and not enough CPU being used to do kind of to your business workload. So so I always ask myself, why isn't it using more CPU, and then try to figure out what's keeping it from doing that, and that usually leads to a pretty good answer. And often it looks a little bit like this. I have a kind of a fun analogy. So I call it the sneaky food truck. So the business model for the sneaky food truck is when you walk up to the food truck and place an order, they dispatch a scooter out the back to go to another restaurant and go have that cooked, and then they bring it back. So it may not be fast, but it's a sneaky food truck. So let's have a look at sometimes it helps when you're thinking about large distributed systems, kind of slow the action down and help figure out what's going on. So you can see this is an obvious analogy here to a service request. So, okay, let's look at how Sneaky Food Truck runs their business. So here's version 1 of it. So version 1 of their run book goes like this. So let's say it takes 1 minute to take the order, and 1 minute to run it over to the restaurant, 10 minutes to cook, and 1 minute to, when you get it back, to package it up and hand it out to the customer. Okay, let's look at some timings and so how they're running their business. So customer walks up at time equals 0, places an order. Order taker takes it, dispatches it out the back. It's to the cook in the diner by minute 2. It's finished by minute 12 and comes back to the order taker by minute 13, and then by minute 14 the customer has their order. Then the order taker takes another order and repeats the same process, and not surprisingly, the second customer gets their order at minute 28. All right, so you could probably spot what's wrong with this picture. If there were, we're going to save the questions for the end, but you can probably spot what's wrong with this picture. So we haven't even used both cooks at the same time, and that's analogous to, your system is not even able to use all the CPU that you have on it. You can't go any faster. So, and the reason is that the order taker is behaving synchronously, right? The order taker is actually waiting for his request to come back before he does anything else. So that's the problem. How could we change it? Well, we could, the order taker could act asynchronously, right? So let's play this a little differently. So t equals 0, the order taker dispatches an order, and it's being cooked by minute 2. Okay, this cook is waiting, but rather than waiting for that to come back, the order taker just turns around and takes the next order. Okay, so and then at minute 2, this second customer has placed their order and it's being cooked by minute 4. So the first order comes back in minute 14, just as before, but the second one comes back at minute 16. We got higher cook utilization or higher CPU utilization, and the whole reason was because the order taker acted asynchronously. All right, so if we look at this as a service, you can, and this is only one single service call, right? If you look at this as a service, you can imagine in this world where we've got microservices calling microservices, and we've got microservices calling, a cache or a database, whatever. You can imagine multiplying this a few times, and you can get a system that it's actually, that has very low throughput, and it's hard to use the CPU because of all the synchronous waiting for remote calls. So hopefully that, so that's a little illustration to kind of provide context for why it's really important to basically dispatch your remote calls asynchronously. And that is, there's a number of ways to do that, but that's kind of an element of this. All right. So now let's look at what is a microservice. And of course, everybody's going to have their own definition, but I think a least common denominator is something along these lines. So as we're decomposing the monolith, we want to break the components up into cohesive business functions. We want them to be independently deployable, and we want them to be composable but loosely coupled. So, if I want to be able to change the implementation of one service without breaking everything that calls it, right? And basically the whole goal of all of this is actually, I think, more than performance is agility. The business wants to be able to innovate, and if they're tied to like back to one monolithic data store, and they have to coordinate everything with everyone, then they're not agile. So that's the essence of a microservice. What's not here, nothing against REST, by the way, but what's not here is REST or application servers. No one, there's no anything that meets this definition, I would say, is a microservice. And does it have to be request response? Of course, a lot of them are, but I have a few examples here for you of microservices that are not request response. So my answer would be no, unsurprisingly. So think about status updates, like notify the customer when their pizza is out for delivery. So yes, you can write an app that checks the status of the pizza, but really, really the ideal thing is for, as soon as that state change happens in the business, for that status update to be pushed out to the customer, or something like tell the customer when their parking is about to expire. Another category of web services that aren't necessarily request response, or services that aren't necessarily request response, is our business process orchestration. So this is things like, so when a customer places an order in online retail setting, for example, you need of course, you need the address of the customer, and you need information about where the actual inventory is located in order to make a plan to fulfill the order. So there's some business process running in the background there that's coordinating all that. And if one warehouse says no, we can't actually fulfill that, another warehouse, that has to be, the pick order has to be sent to a different warehouse. All that needs to be coordinated, and I would say those are also services. And we'd like them to be, microservices, and we don't want them to be part of the monolith. Another example is just releasing held inventory and shopping carts, right? It's not a request response operation, but it is a business process that does have to be orchestrated. So, why not think of that as a service as well? All right, so here's where we're at right now. So first of all, async processing is going to be crucial to the scalability of any distributed system. We saw that with the sneaky food truck. Request response interactions are very common, but they're not the only thing. There's also business processes, status updates, and things that are more naturally modeled as actually just event-mediated interactions between actors, right? Okay, so here's the proposal, and it's not unique. This is not something that's unique. It might be the first time you've seen it. I've seen it for the first time recently, but I think it makes a lot of sense. So what if we were to just treat requests as an event? So as in a request, as in a microservice request or a web service request. What if we just treated that as an event? And then could we just handle all of it in a event processing framework? So that shift allows us to handle everything, the business process orchestration, the status updates, and the request response in the same architecture, an event processing architecture. So they're still so microservices are still deployable, independently deployable units of business logic, but now they're more event processors, right? They're more event processors than they are, request response. And you can fit request response into this framework. So what does that look like? Okay, so I'm going to do a kind of a before and after. So I would say that this is I would say that this is a representation of very high level representation of a typical enterprise stack. And the web services look like this. You've got an app server that's hosting a microservice. There's a caller, and that typically is accessing data from a fast data store or a cache. Could be accessing it directly from a database, but for speed, it seems like most of the time there's some fast data layer in there, and then the fast data layer is synced to the systems of record. It could be read through or it could be synced periodically, depending on how what the data is. But so this is kind of the app server stack, at a very high level. But I put this other stuff on here too, because I think most businesses also process events. So you've got, events coming in from various places, and you've got a message broker and a stream processor to process it. And then those things still need fast data access in order to basically be performant. So you still have that fast data layer as well. Okay, so what the transition would look like this. Okay, so more or less, we've just gotten rid of that box in the bottom left, and we're handling everything now. All the microservices live in this stream processor. Okay, and of course, we're always going to have web services and web service requests. They're very useful, right? So we don't want to completely do away with those. So you could have a caller. You could in theory you could rewrite your callers to send to a request topic and listen on a response topic. But from a practical point of view, you probably still want some kind of you want to access, when you have services that are request response, you want to access them through a web service, or you probably already have those and you don't want to change them, right? So we can kind of put in a shim basically we can put this into a web service proxy to take your HTTP request, turn it into an event, put it on a request topic, and then listen on a response topic. Okay, so so that would be basically a completely event-driven that would be a completely event-driven architecture for your microservices, whether they're request response or whether they're status updates, business process orchestration, whatever they are. Okay, so what technologies are required? So in the message broker area, there's a lot of choices. You basically need something that can basically reliably handle your message, and ideally it's also got replay capability. So we've got Kafka, MQ, Red Panda, all these things, and we also have Hazelcast. So this is something, we have something called map journals that can fulfill that role. Okay, stream processors. So these are newer Kafka, but we're starting to see more and more. We're starting to see lots of these things. They're really propagating. But the ones you might be familiar with, or the ones I was familiar with, at least Kafka Streams, Flink, and also Hazelcast. Okay, and then lastly, the fast data layer. You've got Redis. There's also a lot of these as well. GridGain. There's lots of these, but also Hazelcast. So one of the, being from Hazelcast, one of the things I think is really cool and compelling that makes this architecture even more compelling is if all three of those layers are actually in the same platform. So, so it's the same architecture diagram, but, and it's not three different products. It's like they're in the same runtime, they're in the same JVM. You can even have the stream processor sitting, basically, you can have the event land. We support partitioning just like Kafka does, and you can have the event land in a certain partition and have the data, reference data to process it there and the processing logic there. So, this kind of unified stream processing based architecture, I feel is compelling by itself, but it's more compelling when it's all unified into one platform. All right. So why would we do this? I think I've kind of already hinted at this, but one reason is that we already have stream processing, or we're getting it. It's, and so now that we're adopting stream processing, what if we could basically put all the microservices in that platform? So simplicity and then scalability. So, and this is where we go back to the sneaky food truck lesson. Basically, there are many ways to get asynchronous remote calls. So Spring, we know like Spring supports them very well, but the event-driven architecture is inherently asynchronous. So it's going to basically enforce that all these interactions are happening asynchronously, because you place a message on the message broker and then you're done. You go on and you take the next order and do the next thing. So those are the two main reasons. There's some interesting kind of bonuses as well I want to talk about. Okay, so you can get these. I believe you can get these also with application server based infrastructure or application server based architecture. But I think this is interesting. So I've worked with a lot of different customers, and I always kind of envied, for years, and I've always kind of envied the customers that had event processing systems, because they were easier to upgrade, and we didn't quite have the same, when we needed to do an upgrade, you don't have the same conversations as when it's more of a service, and the service always has to be there. Someone could request at any time, service has always got to be there. So with event processors, right, basically if the event processor, even if it just goes down for just an instant while you upgrade it or something like that, it's just an increased latency. It's not actually an outage. And so it makes upgrades easier. And if you just introduce some kind of, and it's also easy to do like blue-green deployments, because if you just introduce some kind of routing layer, where you've got two implementations of the same service, and they're basically, each one's working off of a different topic or different stream of events, and then the web service proxy can dispatch to either one, and you can use that to get blue-green deployment, and it's pretty easy to do. The other thing is metering and rate limiting. So this is something that we're doing more, we're seeing people do more and more. And metering is something that's very kind of natural in an event, stream processing architecture. It's just counting. It's more or less just counting events, right? Every time I dispatch a response, I can update a counter, maybe specific to the client, whatever. And so metering and rate limiting become, pretty easy problems. And the funny thing is, the other solutions that I've seen to metering and rate limiting usually involve an event processor. They're usually sending events out to something else that processes those events. And it, wouldn't it be, if you're all already within an event processing architecture, then it's kind of easier to do these things. Okay. Oops. And then the other thing, then I think this is actually more when you have your event processor and your fast data store in the same runtime. But when you do have them in the same, it's very common for an event to come in, whether it's a request or something else, and you need, say you're trying to do fraud detection, and this is ML scoring. So, a credit card swipe comes in. Well, you can't make the decision just based on that. You've got to pull in information like maybe recent purchase history and things like that. And that usually comes from your fast data layer. And your fast data layer, if it's actually co-located with the location, in the location where the event's being processed, you can get dramatically higher throughput and lower latency for your event processing. Okay. So I'm working toward a demo, like a prototype of this on Hazelcast. I'd be very interested, at the end of this, to kind of get your thoughts and feedback on this architecture and this approach. I think that over the coming months, we'll be developing this architecture and making it kind of more and more user friendly. So I'd definitely like to get your feedback and your input. But it's always best, I think, to have a real problem that you're working on, or at least some at least facsimile of a real problem. Okay, so here's the setting for the demo and for the problem that and we're going to try to solve with this architecture. So we've got telemetry from a factory floor. It needs to be summarized. For example, what's the average temperature over the last 1 minute of this particular machine. So we want to compute that summary, and we want to make it available as a web service. And we've got, and according to this new definition of microservices, where they could process events, or or they could be actually request response. We've got two services. One is just to digest the telemetry and compute those aggregates, and that's an event-driven service. And then the second one is the status service, and that is our request response service. And the status service is basically going to access those aggregates. So, again, average temperature give me the average temperature of this machine over the last 1 minute. And along with reference data, like, give me as configured, what are the safe boundaries for the temperature reading for this machine? So that's information that's not on the event. It's the information that has to be looked up. So we've got these two services. So it's kind of a simplest possible use case that involves one of each type of service. Okay, and then here's a blueprint of what we're going to see. So I'll start the demo in just a minute. Definitely, it helps to have a blueprint of what you're going to be looking at. So, okay, let's start from the bottom. got all sorts of things popping up over my screen that I can't, so I can't actually see my diagram, but I think I remember what's here. So let's start from the bottom. So I mentioned you've got a factory, it's got machines, they're sending events in. There's all sorts of ways these could get in. It could be over MQTT, it could be Kafka. In this case, we're using our own map journals. Okay, so I've got an event generator, which emulates the factory that's dropping events into a map called machine events. Okay, then a pipeline, we don't have to worry too much about what's in it, but so this whole larger square is a Hazelcast cluster. And these two gray boxes here are pipelines. These are services that we deploy into the cluster, and it runs them in a distributed fashion and so forth. So anyway, one service's job is to compute those aggregates and put those in a map, and then it's called the machine aggregates map. And another service, so that's the first one. And then the second service is a legitimate request response HTTP service. So Hazelcast doesn't directly let you, call web services. So we have this web service proxy that dispatches, just like I was talking about, that dispatches events that are processed by a Hazelcast pipeline. So the requests come into a map that is specifically for this service, for requests from this service. It's processed by a pipeline. The pipeline pulls in this, the current aggregates from the fast data layer here. And then we also want it to do lookups for that are specific to the machine. So the machine ID is in this request, and we're going to pull profile information for the machine. And both of those things are going to end up in the response event that's written back to a map. And the web service and then the web service proxy takes that event and turns it into the web service response. So that's the blueprint of this prototype. Oops, that is not what I wanted to do. Okay, hang on. There we go. Okay. I wanted to back where we started. So I wanted to so one of the things I'm going to demonstrate is blue-green deployment. I just wanted to give a detail on how that works. So basically, the web service proxy will dispatch the request to one of two maps. And you could think of these as topics. They're pretty much equivalent to topics. So it'll dispatch the request to one of two maps, and it does that based on routing information that is in the Hazelcast cluster. And so when you update the routing information, the web service proxy, all the web service proxies are listening, and they will update their dispatching algorithm accordingly. So we can have one pipeline that's servicing version 1 of the service, another pipeline that's servicing version 2 of the service. They can both write back to the same map. But that's how I've implemented blue-green in this POC. Okay. Okay, so now I'm going to start the demo part. Let's switch over. I wanted to quickly show you what the service code looks like now. So the service per se, maybe I can make this a little bigger. Let's get rid of some of that. There we go. There you go. So the service is that I'm using the Spring framework to implement these services, and the Spring async framework. So basically, you can see that this is just a proxy. It doesn't have any business logic in it at all. And let me see if we can go into this. So when we send a request, basically, this is part of the Spring framework deferred result. So basically, we record a deferred result when we send the request, Then we listen for the response, and when the response comes in, it basically completes that deferred result. So the other than a routing logic, the actual web service becomes very, very thin proxy layer. Probably could be generated actually. Okay, so that's the web service layer, and then the actual pipeline. I'll show you that as well. Show you one of them. So Hazelcast pipelines. We won't go into this fully unless someone asks a question about it, but I just kind of wanted to give you a flavor for it. So a Hazelcast pipeline is a deployable jar. You deploy it to the cluster, and what's in it is basically a code definition of a directed acyclic graph. Each step of the graph, you provide your own procedures in terms of, usually with lambdas. So anyway, this is an example of the code for a pipeline. Most of the actual code is in this bit here, where it's basically retrieving the data and formatting it. Okay, so let's actually run the demo now. A little cognitive time. This is all Docker Compose based. So this is gonna spin up a cluster with 2 Hazelcast nodes locally on my desktop. And I need now to get to a web browser. I've got to remove this thing here. There we go. Okay, so this is the Hazelcast Management Center, we call it. It's our UI. And here is the, okay, so here's the main dashboard for the Management Center. All right, so I just wanted to show you a few things before we start. Basically submitting service requests. So we've got a number of maps. A lot of them are about the domain, but some of them are these maps that are being used as topics. So we've got this machine status request version 1 and machine status sorry, I'm trying to get this thing where I can see it. There we go. Machine status request and machine status response. Now, the events are already flowing. So the event-driven half of this demo is actually already running. So let me show you that a little bit. So we have one job that is, like I mentioned, one job is for this machine status service that just simply receives events and retrieves the aggregates. And another job that's computing the aggregates. That's deployed, and you can, that was deployed dynamically when I started Docker. You can see that it is a pipeline, and you can see that we look at this. Boy, that's a little bit finicky there. If you look at this machine status summary map, you can see that it's constantly being updated with the latest status summaries, and we can actually even access these with SQL. So let me do that. Okay, so that's what's in the status summary. Now, I'm going to actually go ahead and call the web service. Now I've got this, obviously I've got this queued up already. So this is Postman. Postman's calling a web service that's also running, that was started when I started Docker. Okay, and we can see it's responding. I've called it a few times. It's responding. It's giving updates. However, we've got this status unknown. So some of the fields aren't filled out. In fact, the data that comes from the reference data lookup basically, isn't filled out. So actually, let's go back to the UI. I should probably copy one of these, get a good one of these. Okay, yeah, so let's go back to the UI and see what's going on now. If we close SQL browser and we look at the maps again, we've got these request and response maps. So basically what was happening is the web service was, or Postman was calling a web service was dispatching an event, and the event was being processed by the pipeline and returned. So now let's actually start. I have a performance test here as well. So let's start that because I want to actually show you an upgrade. So if I, let me change the serial number to that one I just looked up as well. Okay. All right. So I have kind of a dummy service. It doesn't do much right now. We need to upgrade it, but let's upgrade it while everything's running. So I like to use this thing called Locust to do performance testing against web services. It's Python based. It's really cool. That's called the status service. It's running on port 8080 within the cluster. So let's get that going. Yeah, looks like everything is working fine. So basically, this service is going to emulate 20 users, and it's going to basically keep track of our throughput and our latency. And we're just going to leave that running. So looks like our our 95th percentile, that was probably JIT or something like that. So hard to tell for sure. But anyway, our latency is this isn't like 33 milliseconds, something like that. This is all running on Docker. Okay. So now what does it take to do an upgrade now? So let's upgrade this web service. So two things. One is I have to deploy a new pipeline, then I have to update the routing information. I have those scripted in Docker. So let me just quickly show you my Docker compose so you can see that. Okay, so submit summary job 2. This is going to be the job that's going to update the pipeline, and all it's doing is using a Hazelcast CLI to submit a new jar to the cluster. And then we're going to update routing, and update routing is just a program that updates the routing map, just updates the routing information in the map. So let's do those two things now. Did I spell that right? So this is how, this is in this prototype, this is how we would do blue-green deployment. So if I go back to the Hazelcast UI, if I find it, there we go. If I can go back to the Hazelcast UI, look at the jobs. We've got a third job running now. We got summary service 1 and summary service 2. Nothing's going to summary service 1. Everything's going, nothing's going to summary service 2. You can see these are the in and out event counts. Everything's going to summary service 1. So we need to update the routing. And there's no change here either. This is going to be the same. So last bit here, let's just update the routing so that we send work to summary service 2. So what is that? It is load routing config 2. So we still got that performance test running. It's still hitting that web service. That web service is still running. we're just going to like live on the fly update the routing config now. If that all worked, then hopefully I'm going to get something a little different here. Yeah, got something different here. I don't know why that's not updating, but we're actually getting a status here. Actually getting a status here that shows that we updated the web service. And if we look at the performance test, you can see there wasn't a hiccup. It just basically kept on going. So we can, we can just at will. And if we decide, oh, we really need to set that back to the previous version, we can, before I do that, let me just show you the pipeline input queues now. We should, now that we've swapped it over, we look at the pipeline, we could see that, okay, service 2 is receiving traffic now. Okay. So we're doing some things that are, pretty close. I haven't really implemented monitoring, metering here, but we're doing some things that are close to metering, just kind of out of the box. So if we, we can always, if we say, oh, that was a mistake, let's swap back. We can just update the routing configuration, and no hiccups. But we're back to this previous implementation of the web service. And it's all just kind of seamless. So that's really all I have. I think it's kind of an interesting prototype for kind of having a unified architecture that handles both event-driven and request response type services. So I'll just kind of leave it there and see if there's any questions or comments. See if I can open the chat as well.
Thanks, Randy. I don't see anything in the chat box, but is there any questions that anyone would like to ask? Okay.
Yeah.
There is
I
a question.
think, yeah, one person has already asked. So
Okay.
I think, Randy, do you wanna try this first? And then I'll ask.
Absolutely. Yeah. So how do we scale up the stream processor? And this is about an architecture and also about an implementation in Hazelcast. So that's one of the great things is this, whether the stream processor is Flink or if it's Hazelcast, generally speaking, you just scale it up by adding instances. All of these technologies support some kind of partitioning. So basically what ends up happening is you add instances of stream processors, and some of the partitions that were, say right now I have two nodes in my cluster that are doing stream processing. If I add a third node, then that third node starts to consume a subset of the events. And then, like in the case of this machine status, you can see that the problem partitions nicely by machine ID. So basically, you would go from 2 nodes, each handling half of the machine IDs, half of the requests for machine IDs. You would go to 3 nodes, each handling a third. So it's kind of as long as your stream is sharded, or has support for partitions, then it's kind of inherently a scale out architecture. And in the specific case of Hazelcast, basically every time you change the size of the cluster, it redeploys the stream processor, or it redeploys the pipelines that are running in it.
But how do we solve the concurrency issues, Randy?
Yeah, so that's an issue that I haven't talked about today. It's a big topic. So so I guess the first thing is but let's separate out. We don't have concurrency issues when our web services are reading, right? It's really let me not make assumptions. Actually, can you elaborate on concurrency issues?
Let us say in your maybe the monitoring machine example. So let us say a microservice has received two requests for the same machine ID. Okay, and somehow we are processing those two machine IDs concurrently, and there could be a stale update in the database. Okay, which we don't want. Okay, how do we avoid it?
There could be a what in the database? Like a
Or maybe the fast store or whatever you are saying. Okay, so the problem statement is okay, it's a general problem, but I'm just asking, so how do we avoid two requests concurrently being processed inside the inside the microservice of a stream processor? I mean,
that's going to be super specific to the so first I would say if they're both reading, it's probably okay. Certainly in the case of Hazelcast, I know it's okay. I mean, it depends on your architecture, right? It's going to be very architecture specific, but it's perfectly okay for multiple readers, for example, since this data is coming from a map. Perfectly fine for concurrent readers and writers to be accessing the same map key. So yeah, it's not an issue. There are issues though, and so there's a and this is a topic. This is a deep topic. Maybe I'll be able to actually do another talk on this later on, but and another prototype. But a lot of enterprises start by basically having their web services handle read traffic and because until the monolith is fully decomposed, a lot of times their update traffic has to go to the original system of record because there's other things that need to see it, right? So that's something, if that's your case, then you're lucky, right? Because your web services are doing reads. Now, if they're doing updates and they're not idempotent updates, if it's just the map put, you're also okay, because even if in general the way these message processing systems handle failure is they replay. So if they're idempotent updates, you're okay. But if you have non-idempotent updates, now you've got now you have to manage concurrent access somehow, and it's I think it's very problem dependent in that case. But that's a case where it's not an easy problem.
Okay.
Here's some interesting questions here. So what about processing events? Usually a lot more painful to handle errors. Yeah, that is true. So I think what you have to do in that case, and I also think you kind of have to do this anyway, is first of all, you need to model the error in your domain, like in your request and response definition, whether it's an event or if it's like a web service request. You've got to automatically model errors, and then in terms of so basically what I did in this particular case was, again, this is just a prototype, doesn't handle everything by any stretch. But what I did in this particular case is basically if the answer doesn't appear on the topic within basically I think I said 2 seconds or something, then it automatically returns a timeout error. But in general, I think but what if that's not what happened? What if there was some internal processing error? In general, I think you have to basically your pipeline needs to, and I think this is essentially true of any coding model, but your pipeline needs to basically not like blow up. It needs to basically catch exceptions and format them as errors, and that becomes part of the response, and you have to kind of consumers have to know to check for errors and things like that. So I don't think it's
it's me that asked that question. The reason I asked that is I actually worked in system where we were responsible for both asynchronous as well as this request response kind of a thing. And we usually find that when it's asynchronous, we treat each event very important. So if that goes in error, we have processes to make sure that we handle that error. And even in those cases, there are so many errors. Like some teams don't want to look at all the errors. So in those cases, like if it was a request response, the response fails, so there are not many errors to look at. So I was coming from that point of view.
Yeah, no, I get it. I think it is different, and I don't necessarily think I have all the answers to that question. But it definitely is different. The one thing you have going for you in request response is that usually, if you were to drop the event, probably what's going to happen is the caller is going to retry.
Exactly.
I'm out, and the caller retries. So you go, oh well. So, but with so I don't know that it really makes anything worse in that domain, but definitely handling errors. I think that's something that we need to look at as well. And handling errors within pipelines. How do you do that? Like a built-in dead letter queue would be maybe one idea. Things like that. So anyway, so it's a good question.
Thank you.
How do you start to introduce event-driven architecture if you don't have it? Yeah, okay, that's an interesting question. This is from Dale, and I don't know if it's if you would if it's completely hypothetical, or if you have a greenfield project. If you have a greenfield project, you could just start this way, but if not, then I guess you would probably kind of one by one convert. If not, then I'm going to assume that you already have an event processing infrastructure, and you would one by one kind of convert your services over to use it. Strangler fig. Someone tell me about that. I don't know what that is. Although I know what a strangler fig is. Yeah, go ahead.
Yeah, I've not implemented this, but I've read about it.
Yeah.
I think it's basically looking at some functionality within your existing system, and mostly, I mean, you will figure out from your own domain which one it should be. If it is implemented as a request response, then implement that service as an event-driven one, or a microservices based one, and then you should have some sort of a load balancer that will redirect it to this new service that you've written. And once that is successful, you do another one. You keep doing one after the other until all the system moves from your existing monolith or whatever to the new system.
Yeah, kind of pick one off at a time, and that makes sense, because anytime you make an architectural change, it's better to do it gradually, because there's always going to be some kind of surprise, right? It's always going to be some kind of surprise that you haven't thought of. So got any other comments, or I'll just say one other thing. Let me just put it in the chat. If you want to continue the conversation, or if you have other comments, I'd love to hear them. My email is randy.may@hazelcast.com, and the kind of little
I have
proxy.
one more question. I may have missed in the beginning. Is Hazelcast a open source project, or is it?
It's both. So we have open source, and basically our approach with open source is it's great to kind of prototype with. There are actually some customers that are just using open source for production, but basically are like production features, like like in the case of our event processor, being able to stop and restart jobs and save the state of the job. That's an enterprise feature. So we have, in general, we have that approach where we've got the open source. You can pretty much all the APIs are there and work, but there are these like enterprise features that that when you go to production, we're regular licensed product.
Okay.
And we also, by the way, have a kind of, it's called kind of a platform as a service offering, cloud offering called Viridian as well.
Yeah. Thanks.
Okay, so I'm the little dispatcher that turns a request response into an event, for Hazelcast specifically, and works with the Spring Web Services is here if you're interested in playing with that or in contributing to it, enhancing it. So anyway, anything else? Looks like we're right at 2. I guess we need to wrap up.
Thank you, Randy. Yeah, no more questions, I think.
Right, awesome. Hope it's
Hey.
worth your time. Yeah, like I said, reach out to me if you have any comments or questions.
Hey, thank you, Randy. That was very interesting. Yes, as Randy said, if you want to continue the discussion, just reach to Randy or join LJC channels and talk over there. So again, thank you everyone for coming. Thank you, Hazelcast, Chara, and Randy about organizing this event and presenting. And stay in touch and to the next one. Yes. Thank you very much.
Thank you.
Thank you.
Bye.
Bye.